Imagine gazing up at a distant star, 120 light-years away in the constellation Leo, and realizing that one of its planets might be teeming with life. The discovery is breathtaking. There's a 99.7% chance of life on this exoplanet, confirmed by the groundbreaking James Webb Space Telescope. But this isn't some far-flung sci-fi scenario or a planet dotted with cities and satellites. No, this is K218b, an ocean world enveloped in hydrogen, where gases whisper through the atmosphere that we've only ever seen on Earth, and they hint at something alive. This signal could be the key to altering everything we thought we knew about life beyond our planet. K218b resides 120 light-years from Earth. While that may sound like an eternity in the cosmic scale, it's surprisingly close. This mysterious world orbits a faint red dwarf star, K218, located in the constellation Leo, which is roughly 720 trillion miles away. Although red dwarf stars are typically studied in the realm of astronomy, K218 offers something far more intriguing. This star might be home to a planet with the best conditions for life we've ever discovered outside Earth. But to fully appreciate the significance of K218b, we need to understand the star around which it orbits. K218 is a red dwarf, much cooler and smaller than our Sun, and it's one of the most common types of stars in the galaxy, making up about 75% of all stars. These stars burn slowly, living for trillions of years, which means they provide stable energy over incredibly long periods. Good news for any planets orbiting them. However, red dwarfs can flare, emitting bursts of radiation that could hinder the development of life. Fortunately, K218 seems to be relatively calm, giving its planets a better shot at sustaining life. Discovered in 2015 by the Kepler Space Telescope's K2 mission, K218b orbits its red dwarf star every 33 days, much faster than Earth's orbit, but the star is much smaller and cooler. This brings the planet into the so-called habitable zone, or the Goldilocks zone, the perfect distance where conditions might allow water to remain liquid and sustain life. This zone is much closer to the star than it would be for a Sun-like star, which is why K218b's year is only 33 days long. K218b doesn't quite fit into the categories of planets we're familiar with in our own solar system. It's not a rocky world like Earth, nor is it a gas giant like Neptune or Jupiter. Experts propose that it could be what's known as a Haitian world, a planet rich in hydrogen with an ocean beneath its surface. The concept of Haitian planets is relatively new, first introduced in 2021 by researchers like Niku Matadou Sudan at the University of Cambridge. These planets, which are larger than Earth but smaller than Neptune, could still support oceans and, perhaps more importantly, life. K218b is the perfect candidate for this category. Its size and mass are just right to keep a thick atmosphere, but not so big that it becomes a gas giant. Thanks to the infrared data captured by the James Webb Space Telescope, we know that K218b's atmosphere contains water vapor, methane, carbon dioxide, and possibly even dimethyl sulfide DMS, a compound primarily produced by life on Earth, especially in the oceans. This points to the intriguing possibility that K218b's atmosphere could be teeming with biological activity, making it one of the most promising exoplanets to explore for signs of life. Hydrogen is key in making K218b such a fascinating candidate for extraterrestrial life. In a hydrogen-rich atmosphere, the gases that filter through during a transit when K218b passes in front of its star become much easier to detect. Unlike Earth's nitrogen-oxygen atmosphere, which makes it difficult to pick up tiny traces of gases like methane or DMS, a hydrogen atmosphere amplifies these biological signals. Just as hydrogen is crucial for the development of these atmospheres, it also enables scientists to spot trace elements of life. On Earth, microbes can live in extreme conditions, breaking down hydrogen and methane in places like deep-sea volcanic vents. The idea isn't that life on K218b would be like us breathing oxygen and basking in the sun. Instead, life on this distant world might be more like Earth's extremophiles, thriving in a chemical-rich environment. These organisms could be feeding on gases like CO2 or methane in an environment we once thought hostile to life, but which could in fact be ideal for detecting it. The surface of K218b is likely an alien ocean, far from what we know on Earth. The planet sits comfortably in the habitable zone of its star, meaning it has just enough warmth to keep water from freezing or boiling away. However, the unique conditions of this ocean world don't end there. K218b may be tidally locked, meaning it could have a permanent day side and night side. If so, the planet's surface temperatures could vary wildly, creating potentially exotic weather patterns. This idea that K218b could harbor life comes with profound implications. It shifts the search for life from looking for Earth-like planets to exploring the possibility of Hycean worlds, which might be far more common than Earth-like planets in the universe. The discovery of K218b could signal that the universe is far more living than we ever imagined. We no longer need to search for a perfect Earth twin. Instead, we can search for more planets like K218b wrapped in hydrogen, with oceans beneath strange, foreign skies, where biosignatures rise through the clouds. The discovery of K218b's potential for life owes a great deal to the James Webb Space Telescope, JWST. While K218b had already been discovered by the Kepler Space Telescope in 2015, it wasn't until JWST's analysis that we truly realized how extraordinary this exoplanet could be. JWST ripped apart K218b's atmosphere like a crime scene, revealing a host of gases that pointed toward life, something we had never thought possible for a world so far from Earth. What we thought was just another exoplanet in the vast expanse of the universe suddenly became one of the best places to look for alien life. The James Webb Space Telescope's power to analyze distant atmospheres has opened up new frontiers in our search for life. What once seemed improbable now stands as a promising reality. The search for life beyond Earth is no longer just a dream of science fiction. It's a mission we can undertake with the tools we have now. And with K218b, we have a place to begin. The launch of the James Webb Space Telescope, JWST, in December 2021 marked a new chapter in our exploration of the cosmos. By mid-2022, JWST was fully operational, poised to revolutionize our understanding of distant worlds. Equipped with a suite of infrared instruments, JWST can do what no previous telescope has achieved: see through clouds of gas and dust, isolate light with remarkable precision, and detect the faintest chemical traces in exoplanet atmospheres. Unlike its predecessor, the Hubble Space Telescope, which worked in visible and near-infrared wavelengths, JWST is optimized for deep infrared, making it exceptionally sensitive to molecules like water vapor, methane, carbon dioxide, and even dimethyl sulfide DMS, a key signpost for life as we know it. When K218b crosses in front of its host star, an event known as a transit, a small portion of the star's light filters through the planet's atmosphere, offering a glimpse into its composition. That light doesn't just dim, it changes. Molecules in the atmosphere absorb specific wavelengths of light, leaving behind a unique fingerprint that tells scientists what gases are present. Instruments like the near-infrared spectrograph NIRSpec and the near-infrared imager and slitless spectrograph NIRIS aboard JWST are able to detect these subtle changes with unmatched sensitivity. Back in 2019, the Hubble Space Telescope detected hints of water vapor in K218b's atmosphere, sparking excitement across the scientific community. But it wasn't until JWST turned its gaze to K218b that the full scope of the discovery became apparent. The telescope didn't just confirm the presence of water vapor, it revealed the existence of methane and carbon dioxide, signaling a much more complex chemical environment. However, the most groundbreaking revelation came with the detection of dimethyl sulfide, DMS, a sulfur-based compound that, on Earth, is primarily produced by biological processes, particularly by phytoplankton in the oceans. If confirmed, this would be the first time a biosignature gas has been detected on a planet outside of our solar system. Previously, we had detected oxygen or methane on other exoplanets, but always with caveats, and never with this level of precision. JWST's findings shifted the needle from mere possibility to a tangible chance that life could exist in the farthest reaches of the universe. JWST targeted K218b intentionally as part of a program to test its transmission spectroscopy capabilities on potentially habitable worlds. K218b was an ideal candidate because of its size large enough to have an extended atmosphere and its orbit around a faint red dwarf star, which makes the contrast between the planet and its star much easier to read. The data JWST captured was more than just evidence. It was a new level of atmospheric modeling. Scientists didn't just see methane. They saw a combination of methane, carbon dioxide, and DMS, with no sign of ammonia, suggesting that these gases were replenished by living processes, not through simple chemical reactions. JWST's findings didn't just add to the mystery, they deepened it. The combination of gases, the absence of ammonia, and the absence of simpler abiotic explanations pointed to something much more profound, the possibility of life. Scientists didn't just discover what was present, they noticed what was missing. And in doing so, they painted a picture of a planet that could sustain life. The precision of the telescope's instruments reduced the margin for error, making these findings stronger than ever. What's even more exciting is that JWST didn't stop there. This discovery is just the beginning. JWST is part of a longer-term monitoring plan, with more transits scheduled to further refine and confirm these findings. Each subsequent observation will improve the signal-to-noise ratio, ensuring that this groundbreaking discovery is rock solid. For any claim of alien life, no matter how small, no matter how microbial, solid evidence is paramount, and JWST is ensuring that this evidence is as robust as possible. But the telescope's role goes beyond just detecting gases. JWST can also measure temperature, cloud coverage, pressure profiles, and even the vertical layering of the planet's atmosphere. It's as if we're building a weather report for a distant world, one that's 120 light-years away. This unprecedented level of detail could unlock the secrets of K218b and its potential for life in ways that were previously unimaginable. The presence of water vapor on K218b was a monumental moment, more than just water. This discovery marked the first time that we found an exoplanet that might actually be livable. Located in the habitable zone of its star, K218b could have liquid water, a key ingredient for life as we know it. Water vapor isn't rare in the universe. We've detected it in the clouds of Jupiter, in the tails of comets, and even near black holes. But finding water vapor on an exoplanet in the habitable zone is an entirely different matter. Water vapor is a crucial indicator of a life-supporting environment. It's involved in regulating climate, balancing energy, and supporting surface chemistry. If K218b has a water cycle vaporizing, condensing into clouds, raining down, and evaporating again, it could be far more Earth-like than we ever imagined. And that makes it a tantalizing candidate for hosting some form of life. More importantly, water vapor gives us clues about the planet's surface conditions. For water to exist in the atmosphere in significant quantities, K218b must have temperatures and pressures in the right range, not too hot and not too cold. Based on the models created using JWST's data, K218b's temperatures are thought to range between 0 degrees Celsius and 30 degrees Celsius, 32 degrees Fahrenheit to 86 degrees Fahrenheit, an ideal range for liquid water to exist. But K218b is not a replica of Earth. It's much bigger, with a thicker hydrogen-rich atmosphere. Some scientists believe the planet might not even have a solid surface instead. It could be an ocean world beneath a blanket of clouds, a completely different world with conditions we don't fully understand yet. Could this distant world host life? The discovery of water vapor on K218b brings us closer to answering that question. It doesn't confirm oceans, but it strongly suggests that they could exist. This tantalizing prospect of a warm ocean world, with water vapor cycling through its atmosphere, is one of the most exciting possibilities in modern astronomy. The detection of DMS, a molecule that only living organisms produce on Earth, further strengthens the case for life. What was once speculative is now becoming reality. We may have found a planet where life, as we don't know it, could be thriving. The recent discovery of dimethyl sulfide DMS on K218b is more than just a potential breakthrough. It's a revelation that redefines the boundaries of what we think is possible in the search for life beyond Earth. DMS, a sulfur-based compound, is not only rare in the universe, but is produced almost exclusively by life on Earth, particularly by marine phytoplankton. On Earth, this molecule plays a crucial role in cloud formation and climate regulation, a vital process for maintaining life's delicate balance. So, when JWST's instruments detected DMS in the atmosphere of K218b, it was akin to hearing a faint whisper from a mirror world, a distant planet where life might be orchestrating the same atmospheric processes we rely on. The discovery wasn't loud, nor was it accompanied by flashing neon signs declaring aliens here. Instead, it was a subtle feature hidden in the infrared spectrum, among other gases like methane and carbon dioxide. But when scientists ran the models, testing various combinations of molecules against the observed data, DMS emerged as the best fit explanation. That's when things took a turn from speculation to something more grounded in possibility. Unlike methane, which can have both biological and geological origins, DMS has no known abiotic pathway that could explain its presence in a hydrogen-rich atmosphere like K218b's. This makes DMS a tantalizing biosignature, a clue that the planet could harbor life. This finding didn't come alone. Alongside DMS, scientists detected methane, CH4, and carbon dioxide, CO2, two other gases that, when found together with water vapor and DMS, create a chemical fingerprint that screams life. This combination of gases exists in what's known as a dynamic disequilibrium, meaning they need constant replenishment, typically by biological processes, to keep them present in an atmosphere. This trio, water vapor, methane, and DMS, has been dubbed the life fingerprint trio, and on K218b, it paints a picture of a world with a likely global ocean, mild temperatures, and conditions that suggest the presence of biological activity. But, as with all groundbreaking discoveries, science moves forward with caution. The DMS signal is far from confirmed. There is still a possibility that what was detected could be noise, a mistake, or even a signal from a different molecule that was misidentified. The precision of JWST's tools is extraordinary, but no scientific instrument is infallible. The models used to interpret the data are also based on Earth-centric assumptions of biochemistry. And if life on K218b follows an entirely alien set of rules, it might not fit within the expectations we've built. Furthermore, spectral noise distortions in the data caused by instrumental imperfections or cosmic rays adds another layer of uncertainty. This is why the scientific community remains vigilant. While headlines may proclaim DMS possibly detected, there's still a long road ahead before we can say definitively, we've found life. What does this all mean? It means we are standing on the edge of something extraordinary. While DMS on K218b doesn't confirm life, it does make the planet one of the most intriguing candidates we've ever discovered for hosting life. And it challenges us to think differently about where and how life can exist. We no longer need to find a perfect Earth twin to expand our definition of habitability. The presence of gases like DMS, methane, and water vapor suggests that life may thrive in conditions radically different from our own, perhaps in environments we once thought hostile to biology. The discovery raises the stakes for astrobiology. For decades, The gold standard for biosignatures was thought to be oxygen, but we've since learned that oxygen can appear in the absence of life through processes like photodissociation. Methane has been considered a possible sign of life, but it can also be produced geologically. But DMS, it's a rare molecule that is nearly always tied to biological activity. If the presence of DMS on K218b is confirmed, it would mark a historic moment showing that life, as we know it, could exist on a distant world in an entirely different chemical environment. Still, the possibilities remain vast. What kind of life could thrive in an atmosphere dominated by hydrogen? Could it be floating microorganisms, like Earth's airborne microbes, feeding on the gases of K218b's atmosphere? Could it exist in the oceans, beneath a blanket of clouds, feeding on nutrients and releasing sulfur-based gases as waste? Would this life be carbon-based like ours, or something entirely different? These questions remain unanswered, but they are no longer purely speculative. We're now dealing with the real possibility of discovering life, not as a distant fantasy, but as a tangible, scientific pursuit. And that brings us to the 99.7% probability. When scientists say there's a 99.7% chance that the biosignatures detected on K218b are real, it may sound like an assertion of certainty. But what does that actually mean? This number doesn't guarantee life. It's a statistical measure of how well the observed data fits with the hypothesis that biological activity is responsible for the atmospheric composition we see. To get this figure, scientists used Bayesian reasoning, a statistical method that updates our level of belief in a hypothesis based on new evidence. Using this method, scientists compared two models, one where the gases in K218b's atmosphere are the result of abiotic, non-living processes, and one where they're the result of living organisms. The latter model life as the cause fit the data far better, giving a 99.7% probability that life, or at least the signs of it, are present. This is a big deal in science. It's a threshold where excitement begins to build, but the asterisk is important. It doesn't confirm life, but it does mean that the planet's atmosphere is far more likely to be the result of biological activity than not. This level of confidence is huge in the world of science. In physics, it's like reaching the 3 sigma threshold, a point where discoveries start to gain momentum. Though scientists typically wait for 5 sigma confidence 9,999% before calling something a definitive breakthrough. In medicine, it might be enough to start clinical trials. In astronomy, it's enough to start taking the planet seriously as a candidate for life. But the question remains, does life actually exist on K218b? We don't know for sure yet, but we've never been more confident. The next steps involve further observations, more transits, and continuing analysis to strengthen this tantalizing possibility. If DMS turns out to be a true biosignature, then K218b will forever change the way we look at life in the universe. And, perhaps more importantly, it opens the door to the idea that life could exist on planets completely different from Earth, under skies rich in hydrogen, in environments we once believed could never support life. Recent lab studies and theoretical models have presented an exciting possibility. Life could not only survive, but thrive in hydrogen-rich environments. On Earth, there are microorganisms called hydrogenotrophs that directly metabolize hydrogen, converting it into methane or other organic compounds, exactly the same gases that the James Webb Space Telescope JWST detected in K218b's atmosphere. This discovery implies that the basic chemical tools for life already exist in hydrogen-dominated atmospheres, setting the stage for life to emerge. If K218b indeed has an ocean beneath its thick, hydrogen-filled sky, it might very well mirror the conditions that once led to the rise of life on Earth at the critical boundary between ocean and atmosphere, where nutrients, warmth, and chemical gradients are rich and ready to foster microbial ecosystems. The remarkable thing about hydrogen-rich skies is how much easier they make detecting biosignature gases. On Earth, oxygen and nitrogen create tightly packed molecules that absorb only specific wavelengths of light, making it harder to identify trace gases. But hydrogen, being much lighter, creates a more transparent atmosphere, particularly in the infrared. This means gases like methane, DMs, or nitrous oxides stand out more clearly, even at a distance of over 700 trillion miles. This is part of the reason why K218b, despite its vast distance, has provided so much insight with so little helping us see its atmosphere and the potential life-supporting compounds within it. Some have argued that hydrogen-rich atmospheres are unsuitable for life, citing the chemical's reactivity or instability. However, this Earth-centric view misses the mark. We're learning that life doesn't require conditions identical to Earth's. All it needs are energy, a liquid like water, and the ability to engage in organic chemistry. And in environments abundant in hydrogen, prebiotic chemistry can flourish. This is the kind of chemistry that, under the right conditions, can form amino acids, sugars, and even simple nucleotides. Take, for example, the famous Miller-Urey experiment that simulated Earth's early chemical environment, when hydrogen-rich mixtures of gases were exposed to electrical discharges, essentially mimicking lightning organic compounds were created. The implication is profound. Planets like K218b could have all the necessary ingredients for life to start from scratch. But what would life actually look like in such a hydrogen-rich environment? It's unlikely to resemble us. Life on K218b might not breathe oxygen or rely on photosynthesis. Instead, it might exist as microbial mats in the ocean, feeding on chemical gradients between the warm water and the hydrogen-rich atmosphere above. Some scientists speculate it could resemble archaea, one of the oldest and most resilient forms of life on Earth, simple, adaptable, and chemically versatile. And since hydrogen is excellent at trapping heat, it could help sustain life even on the night side of the planet, preventing the oceans from freezing over. This would give life more surface area and more time to evolve, two crucial factors for biological development. Beyond that, hydrogen-rich atmospheres could also help stabilize the planet's climate. Earth's nitrogen-oxygen balance is extremely sensitive, with even small fluctuations in CO2 levels, potentially leading to dramatic temperature shifts. Hydrogen atmospheres, being more flexible and less tightly bound, might prevent these drastic changes, creating a more stable environment over a longer period, giving life more time to emerge and thrive. However, K218b faces challenges from its red dwarf star. Red dwarfs, while abundant and long-lived, are known for their violent stellar flares, outbursts of intense radiation that can strip away a planet's atmosphere and destroy surface life. K218b star, however, appears to be on the quieter side for a red dwarf. It doesn't produce frequent super flares, and its UV output is moderate compared to other red dwarfs. This makes it far more likely that K218b could maintain a stable, life-sustaining environment for billions of years. That being said, we can't entirely rule out the occasional flare. The real question is whether life could adapt or survive such a challenge. The answer may be yes. Life on Earth has adapted to extreme radiation levels over time. Some bacteria can withstand radiation doses that would obliterate most life forms. Others thrive in underground environments, shielded from the sun's harmful rays. If K218b has a thick atmosphere, it could act as a natural radiation shield, absorbing and diffusing harmful radiation before it reaches the planet's surface. This protective atmosphere, combined with potential cloud layers or haze, would create a barrier strong enough to protect life on the surface or in subsurface environments. And if K218b harbors a global ocean, it offers an ideal refuge. Water is an excellent shield against radiation just a few meters below the surface. UV and X-rays are almost completely absorbed on Earth. The extremophiles thrive in similar environments deep beneath the ocean where sunlight never reaches, surviving on chemical energy alone. If K218b has similar underwater environments, It could harbor life forms that never even see their star, living entirely off the chemical energy of their surrounding. But stellar flares aren't just dangerous, they can also create interesting chemical reactions. High-energy radiation from these flares can break apart molecules and create new ones. On Earth, this process was critical in the formation of organic molecules, the building blocks of life. Some researchers suggest that stars like K218b's red dwarf need to be somewhat active for life to start. They need to provide just enough energy to kickstart the chemistry that leads to life, but not so much that it destroys everything. One intriguing possibility is that K218b might have a magnetic field. If the planet has a rotating, conductive interior, it could generate a magnetic dynamo, producing a protective magnetosphere like Earth's. This invisible shield would deflect charged particles and prevent the atmosphere from being stripped away by the star's radiation. While we don't yet know if K218b has such a field, its mass and potential internal heating give it a chance. This, combined with its thick atmosphere, clouds, and possible ocean, means the conditions on K218b may not be as hostile as once thought. In fact, red dwarfs, once considered too unstable for life, are starting to look more promising. New discoveries, like K218b, suggest that, with the right combination of atmospheric protection, magnetic fields, and aquatic environments, planets around red dwarfs could support life, or at least microbial life, far more easily than we previously imagined. Some estimates now suggest that up to 75% of potentially habitable planets in our galaxy orbit red dwarfs. If life can survive in these environments, then life in the universe could be far more common than we ever dared to believe. But the real question remains, what's beneath K218b's clouds? Does it harbor a vast, deep ocean that stretches across the entire planet? Hiding beneath thick clouds and a hydrogen-rich sky, all signs point to that being a very real possibility. If true, it could be one of the most remarkable discoveries in the search for life beyond Earth. And, with future observations, we may soon learn just how much life, or at least the potential for life, exists on this distant world. Recent lab studies and theoretical models have opened up an exciting possibility life could not only survive but thrive in hydrogen-rich environments, like the one found on K218b. On Earth, microorganisms known as hydrogenotrophs directly metabolize hydrogen, turning it into methane or other organic compounds, exactly the same gases that the James Webb Space Telescope JWST has detected in K218b's atmosphere. This discovery implies that the basic chemical conditions necessary for life are already present in hydrogen-dominated atmospheres, creating the perfect setting for life to develop. If K218b indeed has an ocean beneath its thick hydrogen atmosphere, it might mirror the conditions that led to the origin of life on Earth at the crucial boundary between the ocean and the atmosphere, where nutrients, warmth, and chemical gradients are rich, potentially nurturing microbial ecosystems. What makes K218b even more intriguing is the transparency of its hydrogen-rich atmosphere. On Earth, molecules like oxygen and nitrogen absorb only certain wavelengths of light, making it harder to identify trace gases. However, hydrogen, being much lighter, creates a more transparent atmosphere, particularly in the infrared. This allows gases such as methane, DMs, and nitrous oxide to stand out more clearly, even at a distance of over 700 trillion miles. This is why JWST was able to uncover so much information with just a little data, allowing us to peer into an atmosphere 120 light-years away and learn more than we ever expected. Some scientists have argued that hydrogen-rich atmospheres are unsuitable for life because they are chemically unstable or too reactive. However, this Earth-centric view is gradually shifting. We're beginning to understand that life doesn't need Earth-like conditions. It only needs energy, a liquid like water, and the ability to perform organic chemistry. Hydrogen-rich environments, it turns out, can foster prebiotic chemistry, the very kind that can lead to the creation of amino acids. sugars, and even nucleotides. The famous Miller-Urey experiment, which simulated early Earth's chemical environment, showed that hydrogen-rich mixtures could form organic compounds when exposed to electrical discharges, essentially mimicking lightning. This finding suggests that planets like K218b could have all the ingredients needed for life to start from scratch, making it one of the most exciting possibilities for astrobiology. But what would life look like under such a hydrogen sky? It wouldn't resemble life on Earth. Life on K218b might not breathe oxygen or rely on photosynthesis. Instead, it could exist in microbial mats in the ocean, feeding on chemical gradients between the warm ocean and the hydrogen-rich atmosphere above. Some scientists believe it could resemble Archaea, one of Earth's oldest and most resilient life forms. Simple, adaptable, and chemically versatile, life on K218b would likely be highly specialized to its environment. And because hydrogen is excellent at trapping heat, this planet could support life even on the night side, preventing its oceans from freezing over and providing the necessary conditions for biological development. Hydrogen-rich atmospheres may also help stabilize the climate. Earth's nitrogen-oxygen balance is delicate, with even small changes in CO2 levels leading to dramatic temperature shifts. But hydrogen atmospheres are more flexible, providing a buffer against these fluctuations. This flexibility could help create a more stable environment over time, giving life the time it needs to evolve. It would also make the climate on K218b more predictable, giving life more surface area and more time to grow and adapt. However, K218b's star, a red dwarf, introduces a unique challenge. Red dwarfs are known for their violent stellar flares, sudden bursts of radiation that can strip a planet's atmosphere and make it uninhabitable. But K218b star appears to be on the quieter side for a red dwarf. It doesn't produce frequent superflares, and its UV output is moderate compared to other red dwarfs. This is a crucial detail because it suggests that K218b might be able to maintain a stable environment for billions of years. That being said, there's still the possibility of occasional flares, and the question remains whether life could adapt to such challenges. Life on Earth has demonstrated remarkable resilience. Some bacteria can survive extreme radiation levels, and others thrive in environments cut off from sunlight, such as deep underground or near geothermal vents. If K218b has a thick atmosphere, it could shield life from harmful radiation, absorbing and diffusing it before it reaches the planet's surface. This atmospheric armor, combined with potential cloud layers, could make life on the surface or in subsurface environments more protected, even in the face of stellar flares. And if K218b has a global ocean, it could be an ideal refuge for life. Water is an excellent shield against radiation just a few meters below the surface. UV and X-rays are almost completely absorbed. On Earth, extremophiles thrive in deep-sea environments where sunlight never reaches. If K218b has similar conditions, it could host life forms that have never even seen their star, living entirely off chemical energy. Flares aren't just dangerous, they can also catalyze chemical reactions in the atmosphere. These high-energy bursts of light break molecules apart and create new compounds. On Earth, this process was vital for forming organic molecules, the very building blocks of life. In fact, some scientists believe that stars need to be somewhat chaotic in order to kickstart life. Not too calm, but not too violent either, just active enough to stir up the necessary chemistry for life to emerge. K218b's host star might be in this sweet spot, providing just the right amount of energy to initiate life's chemical processes without destroying everything in its path. One intriguing possibility is that K218b could have a magnetic field. If the planet has a rotating, conductive interior, it could generate a magnetic dynamo, producing a protective magnetosphere like Earth's. This invisible shield would deflect charged particles and prevent the atmosphere from being stripped away by the star's radiation. While we don't yet know if K218b has such a field, its mass and potential internal heating give it a fighting chance. With this protection, combined with its thick atmosphere, clouds, and possible ocean, K218b might be more habitable than we previously thought. The real question is, what lies beneath K218b's clouds? Does it harbor a vast, deep ocean that spans the entire planet? Hidden beneath the thick cloud cover and hydrogen-rich sky, all signs suggest that it might, and if it does, it could be one of the most exciting discoveries in the search for extraterrestrial life. We may not have the definitive answers yet, but we are closer than ever to understanding just how life might exist on worlds far beyond our own. Scientists estimate that surface pressures on K218b could range from a few hundred bars to thousands of bars. For perspective, Earth's surface pressure is just 1 bar, while the deepest point on Earth, the Mariana Trench, experiences around 100 bars. K218b's ocean, if it exists, could be under even more extreme pressure depending on how deep it is and how thick its atmosphere is. The good news is that water can remain liquid under high pressure, even at higher temperatures. In fact, this elevated pressure can push the boiling point of water up dramatically. At just 100 bars, water won't boil until it reaches approximately 311 degrees Celsius, 592 degrees Fahrenheit. So, even if K218b is slightly warmer than Earth, the elevated pressure would keep the water stable and liquid, creating a dynamic and potentially habitable environment. But the effect of pressure and temperature isn't confined to just the water, it also alters the chemistry and structure of the atmosphere. Under high pressure, certain gases behave differently. Methane and carbon dioxide, for example, dissolve into water more readily, potentially influencing the ocean's acidity and providing the right chemical conditions for life. At even greater depths, water may enter a supercritical state, where it behaves as both a liquid and a gas simultaneously, an exotic phase that can support complex chemical reactions, which could be crucial for the formation of organic molecules. What would the surface of K218b look like? Most models suggest that it's unlikely to have a solid surface in the way we think of Earth's crust. Instead, K218b could be a world covered by a vast, deep ocean, with strange ice or silicate rock lying far beneath it. The upper layers might be veiled in clouds and fog, with thick hydrogen clouds reflecting light and keeping temperature fluctuations to a minimum. The interface between the ocean and the atmosphere, where liquid water meets the air, would be key. This is where light, heat, gases, and liquid all meet and interact, making it an ideal location for the formation of biosignatures, like dimethyl sulfide DMS. If microbial life exists on K218b, this turbulent boundary layer is likely where it would thrive, living off temperature gradients, dissolved gases, and access to both light and nutrients. Could K218b be tidally locked, with one side always facing its star and the other in permanent darkness? It's possible, but not necessarily a deal breaker for life. A thick atmosphere like K218b's can efficiently redistribute heat, especially with hydrogen, which is excellent at conducting thermal energy. Climate models suggest that the planet could maintain stable temperatures across the entire planet, even if one side is constantly exposed to the star while the other remains in eternal night. Ocean currents, wind patterns, and atmospheric circulation would help smooth out extreme temperature differences. With enough internal heating, possibly from tidal forces or radioactive decay, the ocean could remain warm at depth, creating an environment for life to persist without direct starlight, much like life on Earth's deep-sea hydrothermal vents. This potential stability of K218b's climate, along with its internal heating and possible liquid oceans, makes it one of the most promising candidates for supporting life beyond Earth. Scientists believe that K218b's thick atmosphere, ocean, and potential internal heating mechanisms could keep the ocean's surface stable and liquid over geological timescales. The question is not just whether liquid water could exist, but whether the planet can maintain the delicate balance required for life to emerge and persist. Further data and observations from JWST and other telescopes will continue to refine our understanding of K218b's potential for life. The team of scientists is looking at everything from its atmospheric composition to its surface pressure and temperature to build a fuller picture of what this distant ocean world might hold. With each new discovery, we edge closer to an answer to the ultimate question: could life, as we know it or in some other form, truly exist on K218b? The possibility is no longer a distant dream, but a real and tangible mystery waiting to be unraveled. Scientists don't simply look through a space telescope and read labels from the clouds to detect gases like methane or dimethyl sulfide, DMS on K218b. Instead, they rely on sophisticated models of the planet's atmosphere, using data from the light that passes through it during a transit. This light interacts with the planet's atmosphere, and the resulting spectrum, a series of light data, contains vital clues about the molecules present. However, understanding this spectrum is far from straightforward. It's filled with noise and interference, and scientists have to carefully work through these complexities. One of the key tools in deciphering this information is the radiative transfer model. These are high-level simulations that track how light moves through a planet's atmosphere. The models simulate how different gases absorb light at different wavelengths, like how methane absorbs strongly at around 3 microns in the infrared, water vapor at 1, 4, and 1, 9 microns, and DMS at its specific bands. Scientists then compare these simulated results with the data collected by the James Webb Space Telescope, JWST. This allows them to match patterns and narrow down what gases could be present in the atmosphere. The more accurately the simulated spectrum fits the observed data, the more likely the atmospheric composition it suggests is correct. But atmospheric modeling isn't just about understanding gases. It's a complex task that also requires accounting for temperature gradients, pressure profiles, cloud opacity, and altitude-dependent chemical reactions. For K218b, these simulations are particularly difficult due to its hydrogen-rich atmosphere and possibly thick cloud cover. Additionally, the presence of supercritical fluids and unfamiliar chemistry adds layers of complexity to the process. The models need to capture an entirely different environment than anything we have on Earth. Here, Bayesian statistics come into play. Scientists use these statistical tools to test millions of atmospheric combinations, comparing each one against the data. The model that best matches the observed spectra is ranked highest, but this doesn't mean it's guaranteed to be the truth. It simply means that it's the most likely explanation based on current knowledge. This process, known as retrieval modeling, is extremely demanding. Some simulations can take weeks to run. Supercomputers and cloud platforms are often used to handle the vast amounts of calculations needed. Thousands of possible atmospheric scenarios are tested, with slight variations in conditions, to see which one best fits the data. For instance, scientists might explore scenarios where DMS is absent, but methane and carbon dioxide remain, or whether the observed spectrum could be explained by abiotic processes alone. They might also test what changes occur if the clouds are thicker or if the atmosphere contains more nitrogen than expected. It's a methodical, complex process that ultimately gives scientists the most probable answer they can rely on. But it's far from a simple task. As with all scientific endeavors, the more data collected, the more confident researchers can become in their findings. In the case of K218b, these simulations are crucial for determining whether the biosignature gases we've observed, methane, carbon dioxide, and DMS, are truly indicative of life, or whether they're products of exotic, non-biological chemistry. The next few years of transits and data collection will be essential to confirming or refuting the current hypothesis. While there's still much to learn about K218b, the sheer potential of the planet continues to spark excitement among scientists and astrobiologists. The combination of a hydrogen-rich atmosphere, a possible global ocean, and the presence of gases like methane, TO2, and DMS make it a prime candidate for studying life beyond Earth. For now, the search continues, with every new observation inching us closer to an answer. K218b might just be the key to understanding the broader possibilities of life in the universe. Each new transit of K218b helps scientists refine their understanding, gradually narrowing down the possibilities and inching them closer to answering the big questions about life on this distant world. The models they build for these atmospheres, powered by sophisticated simulations, are complex but essential. They involve creating thousands of possible scenarios and comparing the resulting spectra to what JWST actually observed. The more variables included, the more accurate the predictions. But it also makes the task more difficult. One of the biggest challenges in atmospheric modeling is dealing with degeneracy, the phenomenon where different combinations of gases can produce similar spectral patterns. For example, methane and carbon dioxide might look the same as methane with less cloud cover. The fingerprint of DMS could resemble a rare sulfur molecule we've yet to identify. This is why the trust numbers, like the 99.7% confident, are so important. They provide a statistical validation, showing how much more likely one explanation is over another. Clouds and haze also add a layer of complexity. Thick cloud layers, possibly made up of water droplets, hydrocarbons, or exotic ices, can obscure or flatten spectral features, making it difficult to detect small molecules. K218b, with its thick atmosphere, likely has such clouds, which dramatically influence the light passing through. To ensure their model's accuracy, scientists cross-check these simulations with Earth-based lab data, refining them as more research is done. The dedication to unraveling these atmospheric mysteries is extraordinary. Millions of models, weeks of computer time, and complex chemistry are all used to interpret the faintest dips in starlight. But those seemingly small dips hold incredible information. They reveal not only the gases in K218b's atmosphere, but also how much of each gas is present, where they reside, and what the temperature is like. And astonishingly, all of this information is obtained without even capturing a direct image of the planet. However, despite the excitement surrounding the possible detection of DMS, the signal still comes with uncertainty. Could it be a false alarm? The detection was based on the analysis of starlight passing through K218b's atmosphere during its transit, which is then examined for patterns that match the signatures of specific gases. DMS has a distinct absorption feature in the infrared spectrum, but so do other molecules, and some can overlap. The DMS signal could, in theory, be a result of a mix of gases, especially if K218b's hydrogen-rich atmosphere contains chemicals not yet studied. Additionally, there's always the possibility of instrumental noise, tiny artifacts caused by cosmic rays, detector sensitivities, or thermal fluctuations, which could be mistaken for genuine signals. The signal's faintness, along with the limited number of transits analyzed so far, means that it's important to be cautious. A higher signal-to-noise ratio, achievable through more observations, is necessary to confirm whether DMS is truly present. Scientists need to ensure the data is consistent across multiple transits, using different instruments and wavelengths to improve the reliability of the results. This uncertainty is why the signal is still labeled as a biosignature candidate rather than proof of life. Future transits, scheduled for 2026 and beyond, will provide the data needed to either confirm or revise the hypothesis. Longer exposure times, refined calibration, and improved targeting precision will help pinpoint whether DMS appears consistently. These new observations will also allow for better estimates of the abundance of methane, carbon dioxide, and water vapor, further clarifying whether K218b's atmosphere contains a mix of gases that defy abiotic explanations. Scientists will also focus on the structure of the clouds, which remain one of the most uncertain aspects of the models. Understanding the composition and distribution of clouds could reveal important details about atmospheric dynamics and the potential for biological processes. As more data is collected, astronomers will continue to probe deeper into K218b's atmosphere, mapping its vertical layers and studying the distribution of gases at different altitudes. This can help identify whether gases like methane are concentrated near the ocean-atmosphere interface, which would point to biological activity. Observatories like Hubble will play supporting roles, monitoring the star K218 for UV activity and providing additional insights into the environment surrounding this intriguing planet. The story of K218b is far from over. With each new observation, the possibility of discovering life, no matter how alien or unfamiliar, grows more tangible. Every piece of data, every observation, brings us closer to understanding the true nature of this distant world. And while we can't yet say with certainty that life exists on K218b, the evidence continues to mount, making this world one of the most promising candidates in the search for life beyond Earth. Instead, the heat from the day side would likely be transported through the thick atmosphere, keeping the night side warmer than we might expect. The constant atmospheric circulation, combined with the high thermal conductivity of hydrogen, could stabilize temperatures across the planet, preventing extreme freezing on the dark side. This dynamic atmosphere would promote a sort of continuous exchange, with powerful winds and cloud formations sweeping across K218b. The resulting weather systems could be incredibly dramatic, with intense storms forming at the boundary between the illuminated and dark sides, where heat differences would create strong temperature gradients. It's possible that lightning could frequently strike these regions, igniting fierce electrical storms as the atmosphere moves to balance out the thermal extremes. These storms could be massive, dwarfing anything seen on Earth, with clouds charged with electricity and winds reaching hundreds of kilometers per hour. At the edges of these storms, you could witness the clash of day and night, creating tumultuous conditions that would drive the dynamic weather on K218b. On the night side, the situation would be calmer, with no direct light from the star, but even so, the ocean might still gently reflect the star-filled sky above, creating a tranquil but eerie landscape. Without a moon, there would be no natural light to break the darkness, making the night side of the planet an incredibly dark and serene environment. However, the ocean could still be warmer beneath the clouds, sustained by the deep, insulating layers of the atmosphere. In terms of its appearance from space, K218b would likely not resemble the blue of Earth or the reddish hue of Mars. With its thick, hydrogen-rich atmosphere and reflective haze, the planet could appear pale white, greyish, or possibly even pink-tinged, particularly when illuminated by the dim light of its red dwarf star. Its cloud tops might be thick and persistent, and the planet's infrared signature would likely make it glow faintly, giving it an almost ghostly appearance in the thermal wavelengths. As scientists continue to analyze data from the James Webb Space Telescope and other observatories, the full picture of K218b's atmosphere and its potential for habitability will continue to emerge. The next set of observations and data, along with new models and simulations, will be key in determining whether this strange, distant world could harbor life. K218b represents one of the most exciting discoveries in the search for life beyond Earth, with its potential for microbial life thriving in the alien conditions of its hydrogen-rich atmosphere and deep oceans. With more research, the dream of finding life on other worlds becomes more tangible, and K218b may just be the key to unlocking the mysteries of life in the universe. TOI 700d is another exoplanet in the search for extraterrestrial life, and it offers an intriguing comparison to K218b, located in the TOI 700 system, about 100 light-years away. TOI 700d orbits a much cooler star, a M dwarf similar to K218's red dwarf, but with one significant difference. TOI 700d has a much smaller size and a potentially rocky surface. This makes it more Earth-like in terms of composition, with a radius roughly 2 times that of Earth. It is considered a prime candidate for habitability due to its location in the habitable zone of its star, where liquid water could exist on its surface. While TOI 700d has similar advantages in terms of its distance from its star, It lacks the substantial hydrogen-rich atmosphere that K218b possesses, which plays a key role in the planet's potential to harbor life. The thinner atmosphere of TOI 700d, in contrast, might not provide the same level of protection or climate stability. Without this thick atmosphere, TOI 700d would be more vulnerable to stellar radiation, especially from its relatively active star, and the planet's thinner atmosphere would also make it more difficult to detect any biosignatures. This difference in atmospheric characteristics highlights a fundamental challenge in comparing exoplanets for habitability. While TOI 700d's size and location in the habitable zone make it a compelling candidate, the planet's less substantial atmosphere could limit our ability to detect and sustain life. In contrast, K218b's thick hydrogen-rich atmosphere provides a more robust shield, not only offering better protection against radiation, but also allowing for a clearer spectral signature, a crucial factor in the search for biosignatures. These differences underscore the unique potential of K218b as a target for studying life beyond Earth. In essence, while TOI 700d and other Earth-like exoplanets are fascinating due to their composition and proximity to their stars, K218b's thick atmosphere, larger size, and unique environmental conditions make it an ideal candidate for astrobiological research. The presence of methane, carbon dioxide, water vapor, and potentially dimethyl sulfide DMS in its atmosphere already places K218b at the forefront of exoplanet studies. If the DMS signal is confirmed, it would be a groundbreaking discovery, showing us that a planet with an entirely different atmosphere could still harbor life in ways we hadn't considered before. As we continue to refine our observations, K218b remains an exceptional case in the search for life beyond Earth. The ongoing studies from the James Webb Space Telescope, along with future missions, will provide invaluable data to help us better understand this alien world, its potential to support life, and how we can expand our understanding of habitable conditions in the universe. The future of planetary science is filled with possibilities, and K218b is one of the most exciting places to look for the answers. With the potential for seasonal changes, K218b could reveal one of the most profound and unique signatures of life outside our solar system. If microbial life exists there, even in the form of plankton or other microscopic organisms, the planet's atmosphere might display subtle but measurable fluctuations in gases like methane, oxygen, or dimethyl sulfide DMS. These variations could occur in sync with seasonal cycles, giving us a glimpse into the biological activity that might drive these changes. Tracking these seasonal shifts over time, astronomers could build a dynamic profile of K218b's atmosphere, revealing patterns that point to life's rhythms. It's not unlike what we see on Earth. Carbon dioxide levels rise and fall with the seasons. Photosynthesis peaks during certain times of the year, and even the changing of plant and animal activity leaves detectable marks. On K218b, seasonal variations could occur as microbial life blooms and decays in the planet's oceans, or as atmospheric dynamics shift between day and night, and between the planet's permanent light and dark sides. Even in the absence of visible life, the planet's atmosphere itself might show signs of seasonal change. Cloud cover, haze, and ocean evaporation could change with the passage of time. This would give scientists valuable data about how K218b's climate shifts and whether its ocean remains stable despite the extreme conditions. The ability to track seasonal changes in exoplanet atmospheres will open a new era of astrobiological exploration. In the case of K218b, while we're still in the early stages of these observations, the potential for discovering such patterns is immense. If we can detect these seasonal trends, we may be able to not only identify the conditions that could sustain life, but also begin to unravel the intricate biological processes that make alien life possible. The key to this is continued monitoring, using both current and future telescopes, such as the James Webb Space Telescope, to track changes over the course of several years. This concept of detecting seasonal changes is far from science fiction. It's a real possibility, already being tested in earthbound studies that simulate how planets might behave when viewed from afar. These methods are designed to help us learn not just about the atmosphere, but also about the potential for life beneath the clouds, on the surface, or in the oceans of distant worlds. The next few years of study will be crucial. As JWST and other future instruments collect more data, we'll refine our understanding of K218b and its potential for supporting life. Each new observation, each additional year of data, brings us closer to answering the age-old question, are we alone in the universe? With K218b, the search for extraterrestrial life takes on new meaning, offering us a window into a world so different from our own, yet possibly sharing the same fundamental conditions that make life possible. K218b's potential for a magnetic field is a crucial factor in determining whether it can maintain its thick hydrogen-rich atmosphere long-term. If K218b does have a magnetic field, it would act as a protective shield, deflecting the harsh radiation from its red dwarf star and preventing atmospheric loss. This could significantly improve the planet's chances of maintaining stable conditions for billions of years, ensuring that life, if it exists, remains safe from the damaging effects of stellar radiation. A magnetic field on K218b would likely be generated by the movement of molten metals in its core, much like Earth's magnetic field. The size and mass of K218b increased the likelihood that it could generate a powerful dynamo effect, potentially creating a stronger magnetic field than Earth's. However, if K218b is tidally locked where one side always faces the star, the planet's rotation might be slow enough to prevent a geodynamo from forming. This is why scientists are cautious, as the lack of a magnetic field would leave the planet vulnerable to the stripping effects of stellar winds, cosmic radiation, and X-rays from its red dwarf star. Without this protective magnetic field, the atmosphere of K218b would be at risk of being slowly eroded by the radiation from its star. However, if the planet does possess a magnetic field, even a mild level of stellar flaring from its host star would be less likely to strip away the atmosphere. In this case, K218b would be able to maintain its hydrogen-rich atmosphere for a much longer period, keeping the environment stable and potentially habitable. The possibility of a magnetic field also ties into K218b's broader potential for sustaining life. The planet's ability to keep its atmosphere intact, whether through the protection of a magnetic field or other mechanisms, would play a major role in determining if life could exist on the planet. Even if life is hidden beneath K218b's surface, the preservation of a stable atmosphere could allow for the long-term evolution of microbial ecosystems, similar to those found around hydrothermal vents on Earth. As our understanding of K218b continues to evolve, the presence of a magnetic field will be a key area of study. Observations from telescopes like JWST and future missions could shed light on whether K218b's magnetic field is strong enough to protect its atmosphere and support a stable environment for life. Until then, the ongoing study of this fascinating world and its unique characteristics will provide us with valuable insights into the potential for life on exoplanets, especially those that, like K218b, offer more mysteries than answers. If K218b hosts intelligent life, the signals we might receive would likely be radio waves, laser pulses, or other forms of electromagnetic communication. These methods of transmission are the most efficient known to us for interstellar communication, as they can travel vast distances without significant loss of signal strength. However, as discussed, the delay in communication would be substantial due to the vast distance between Earth and K218b, approximately 120 light-years away. If a message were sent from K218b, it would take 120 years to reach Earth, and any response from us would take another 120 years to get back to them, creating a 240-year communication cycle for a single exchange. This long delay underscores the challenges faced by efforts to communicate with potential extraterrestrial civilizations. It also highlights the deep time gap that would exist between any advanced civilization on K218b and our current level of technology. For example, if a civilization on K218b had sent a message in the early 20th century, we'd only be receiving it now, a century later. The implications of this delay are profound for the search for extraterrestrial intelligence SETI. If K218b's intelligent civilization had already disappeared or evolved in a radically different direction, we might never even hear from them. Even if they are still around, any response we send would reach them only after centuries. The gap between technological eras could make any communication between us almost like a message in a bottle, sent across space, and waiting for a reply that may never come. Given this immense time delay, it is also worth considering the potential for civilizations to change or evolve drastically in the time it takes for messages to be received and responded to. By the time we could communicate with them, their technology or society might have undergone such a transformation that they are unrecognizable to us. The concept of interstellar communication is not just about how quickly we can send signals, it's about how much we can learn from signals sent long ago. It is possible that civilizations far from Earth have already reached their peak or declined, leaving behind signals from their past signals we might now intercept, even if they no longer exist in the form they once did. In addition to communication delays, there is also the question of the form of communication. The methods used to send information between civilizations may evolve beyond our current understanding, potentially using frequencies or technologies that are still unknown to us. Nonetheless, the search for intelligent life remains a tantalizing, if distant, pursuit, driven by the hope that somewhere in the vastness of space, a civilization on K218b or another distant world is listening, waiting for a message from Earth. In the meantime, studying planets like K218b offers us valuable insights into the potential for life beyond our planet. Whether life on K218b is microbial, intelligent, or somewhere in between, its study brings us closer to answering some of humanity's most profound questions. Are we alone in the universe? And if not, what might life on other worlds look like? Nulling interferometry is another innovative technique that could help us observe exoplanets like K218b directly. It works by combining the light from multiple telescopes, creating an interference pattern that cancels out the light from the host star, while allowing the faint light from the planet to pass through. This technique could provide unprecedented detail about planets like K218b, allowing us to observe features like cloud pattern, atmospheric composition, and potentially even signs of artificial lights on the surface, something we might not be able to detect with current methods. While this method is still in development, future missions could use this approach to gain a clearer image of planets within habitable zones. Like K218b, this type of imaging could reveal a whole new level of information about alien worlds, potentially allowing us to see surface features, seasonal changes, or even detect technological activity that signals intelligent life. In the meantime, JWST and other current telescopes will continue to collect valuable data on K218b, focusing on its atmosphere, chemical signatures, and the conditions that might support life. However, the ability to directly image the planet is still a long-term goal. With advancements in space telescope technology, such as LUVOIR or HABEX, we could begin to see clearer, more detailed images of exoplanets within the next couple of decades, providing a glimpse into the worlds that could harbor life or evidence of it. As for the search for technosignatures, detecting artificial light or signs of advanced technology on planets like K218b would take patience and advanced tools. Future telescopes equipped with more precise instruments could potentially spot such signals, but the chances of detecting them will depend on a multitude of factors: the alignment of the planet's signals with our instruments, the type of technology used by the alien civilization, and the complexity of the communication methods. In the quest for life beyond Earth, it's clear that planets like K218b, with their intriguing atmospheric signatures and potential for subsurface ecosystems, offer one of the most exciting possibilities, whether through detecting biosignatures, techno-signatures, or eventually using direct imaging techniques. K218b represents a prime target for astrobiologists and astronomers alike. Its study could one day change our understanding of life in the universe and reveal whether we are truly alone or part of a much larger cosmic community. K218b represents a crucial turning point in the field of astrobiology for several key reasons. First and foremost, it's the first exoplanet to show clear signs of biological activity with multiple potential biosignatures detected in its atmosphere, including methane, carbon dioxide, and dimethyl sulfide DMS. This combination of gases, particularly DMS, which is closely linked to life on Earth, raises the possibility that K218b could harbor microbial life, or at the very least, have the conditions needed for life to emerge. What makes K218b so pivotal is that it challenges our traditional understanding of habitability. While we have focused on finding Earth-like planets with rocky surfaces and oxygen-rich atmospheres, K218b shows that worlds with thick hydrogen-rich atmospheres and deep oceans could also be prime candidates for life. These planets may have the potential for stable environments over long periods, making them not only a fertile ground for life, but also a valuable target for future astrobiological studies. Furthermore, the study of K218b pushes the boundaries of how we detect and interpret biosignatures. With the advent of advanced telescopes like the James Webb Space Telescope JWST, we now have the ability to analyze the atmospheres of exoplanets in unprecedented detail. K218b has opened up new methods of detection, from spectral analysis to secondary eclipse measurements, and possibly even direct imaging in the future. This progress in observational technology could eventually lead to the discovery of more life-supporting worlds and even the direct detection of alien life. K218b is also a test case for our scientific models. The possibility of life in its deep oceans, protected by a thick atmosphere and shielded from harmful radiation, presents a unique set of challenges and opportunities for astrobiology. Experiments on Earth are already simulating the atmospheric conditions of K218b to understand how gases like DMS could form, and how biological and non-biological processes contribute to the planet's chemistry. These Earthbound simulations are helping to refine our understanding of how life could emerge in different environments, both within our solar system and beyond. Moreover, K218b highlights the importance of time in the search for life. The planet's red dwarf star has allowed it to exist for billions of years, providing more time for life to evolve and adapt. This extended time frame may give rise to complex, possibly intelligent life forms. The presence of such life would change the entire field of astrobiology, offering insights into the diversity of life forms that might exist in the universe. As scientists continue to study K218b and its potential for life, they may uncover entirely new forms of biology that operate on principles different from what we know on Earth. In conclusion, K218b isn't just another exoplanet. It represents the beginning of a new era in the search for life beyond Earth. It challenges our assumptions, tests our technology, and forces us to reconsider what makes a planet habitable. Whether or not K218b harbors life, its study is already reshaping our understanding of the universe, and the methods developed in its exploration will shape the future of astrobiology for generations to come. Astrobiology has indeed come a long way, evolving from early speculations about Martians to the sophisticated study of distant worlds, and K218b marks an important chapter in this journey. This planet, once just another red dwarf world, has now become a beacon in the search for life beyond Earth, not because it closely resembles our planet, but because of its unique, unexpected characteristics that may hold the key to understanding the potential for life elsewhere in the universe. The discovery of methane, carbon dioxide, and possibly dimethyl sulfide DMS in K218b's atmosphere is groundbreaking. While this does not confirm the presence of life, It marks the first time that biosignature candidates have been detected in the habitable zone of an exoplanet by a telescope, specifically the James Webb Space Telescope, JWST. This is a significant upgrade from past exoplanet discoveries, where life was often speculated based on indirect measurements, assumptions, and Earth-like analogies. What makes K218b particularly exciting is that it doesn't fit the mold of an Earth-like planet. It is not a rocky world with blue oceans and continents. Rather, it is a high-end world, a hybrid planet with a thick, hydrogen-rich atmosphere and possibly a deep global ocean. This class of planet, which includes worlds like K218b, wasn't even part of the official planetary science lexicon until recently, despite being radically different from Earth. These high-end worlds could be even more habitable in some ways, offering a fresh perspective on what constitutes a potentially life-supporting environment. K218b challenges our Earth-centered bias in science. For decades, researchers focused on planets with Earth-like characteristics, rocky surfaces, thin atmospheres, and liquid water when looking for life. However, K218b's discovery forces scientists to reconsider. Life might not need the same conditions that Earth provides. It might survive in atmospheres thick with hydrogen, relying on metabolisms and chemical processes vastly different from what we know. This opens up new avenues for astrobiology, suggesting that life might thrive in environments previously dismissed. The scientific community has quickly realized the importance of K218b as a testbed for new ideas in astrobiology. The detection of key molecules such as methane and carbon dioxide in its atmosphere, along with the possible presence of DMS, is helping to recalibrate theoretical models about biosignatures and habitability. Experiments are being redesigned to understand how life could exist in such alien conditions, and new exoplanet survey strategies are emerging, with more attention being given to high-end worlds like K218b. The implications of K218b go beyond just the search for life. They represent a psychological shift in the scientific community. The search for life beyond Earth was once viewed as speculative or distant. But K218b offers a solid, real-world dataset, a reason to ask the question of extraterrestrial life not just philosophically, but scientifically. NASA, ESA, and universities are all treating K218b as more than just another planet. It's becoming a case study, bringing together astronomy, chemistry, biology, and planetary science into a real-world investigation of life's potential across the cosmos. However, with excitement comes caution. The 99.7% probability of life on K218b, based on the initial data, is still not definitive. Science is built on skepticism and repetition, and the coming years of observations will either confirm or challenge these findings. The DMS signal, while exciting, is tentative. The scientific community remains cautious, as history has shown that early detections of biosignatures can sometimes turn out to be false positives. The next wave of data, expected between 2026 and 2027, will help refine or challenge these initial conclusions. K218b's potential for life is just one part of the story. Even if the DMS signal vanishes or proves to be something else, the detection of methane, carbon dioxide, and water vapor is still highly significant. These molecules alone make K218b one of the most promising exoplanets ever discovered, and the potential for life, however improbable, is still worth investigating. Moreover, K218b is just the beginning. It opens the door to the exploration of other high-end worlds, which are more common than previously thought. These planets, with thick hydrogen atmospheres and deep oceans, could be more stable and hospitable for life than rocky, Earth-like exoplanets. If K218b is an anomaly, it's an anomaly that we may find repeated across the galaxy. In conclusion, K218b represents a pivotal moment in the search for life beyond Earth. It challenges our assumptions, pushes the boundaries of our observational tools, and forces us to think outside the box when it comes to the conditions required for life. Whether or not life exists on K218b, its discovery has already reshaped the way we look at the universe, and it promises to change the way we search for life in the cosmos for years to come. K218b may not be the final answer, but it's a vital step toward finding the true diversity of life in the universe.